So they discovered electrons. That led to more questions. Much of science, doing research is like being an ant crawling up a very large tree. And you come to a branch and you go off over here and you keep coming to branching points where you've got all these questions. You have to choose one to investigate. If you ever end up at the end of a leaf, all you have to do is backtrack a little bit and go off on a different branch. There's an endless amount of stuff that can be studied. So some of the questions this led to is, well, if there's a negative charge, there must be a positive charge because we know these things are neutral. And how does that work? How do those fit together? Are atoms really just a jumble of even more fundamental particles? So atoms have electrons. Are there other particles in there? Are atoms solid spheres? Do they have some internal structure? What's going on here? So Thomson came up with a plum pudding model. You have to start somewhere. Plum pudding model to describe what's going on with the negative electrons and this unknown positive stuff. Because we don't eat plum pudding in the United States. I wouldn't recognize it even if I saw it. The closest thing that we would recognize would be a blueberry muffin. So we've all probably seen a blueberry muffin. So this is like a blueberry muffin where this red part here, which is the positive charge area, would be like the muffin part. And the electrons would be like the blueberries. Okay, so the blueberries are just kind of randomly distributed through the muffin. The electrons are just sort of randomly distributed. You got to start somewhere. So this was his idea, and then he tested it. Before we can talk about how he tested it, we have to do a little bit of learning about radioactivity. Radioactivity will be covered more in depth in Chem 1B, and that's in Chapter 20. It might be Chapter 21 in your textbook. So we're just going to do a little bit here. Radioactivity is the emission of small energetic particles from the core of certain unstable nuclei. It was discovered at the end of the 19th century by Henri Becquerel and Marie Curie, whom you've probably heard of. The discovery of radioactivity was important because it allowed scientists to probe the structure of the atom. There are actually four types of radiation. We're only going to talk about three. Oh, that should be three types. Alpha particles, beta particles, and gamma rays. Alpha particles are positively charged, and they are the most massive of those kinds of radioactivity. Okay, so now that we have a clue about what alpha particles are, in 1909, Ernest Rutherford, he had worked with Thomson. He was not trying to disprove Thomson. He thought, well, the plum pudding model, this is fine. And so he's doing an experiment trying to confirm this, and he ended up blowing it out of the water. So in this experiment, he took some positively charged alpha particles, so radioactive emissions, and he sent a stream of these at an ultra-thin sheet of gold foil. The plum pudding model predicted that these particles would just go straight through it. Here's an illustration of his setup. Here's the source for those alpha particles, and he made a beam, and he's directing it at this very thin sheet of gold foil, expecting that they're just going to go straight through. Got a detector, a circular detector set up so that we can see where they go. Most of them did go straight through. Some of them got bent a little bit, but some of them bounced back. They were deflected at very large angles, and that was pretty shocking. So most of the particles went through as expected, but about 1 in 2,000 bounced back. And he said this was about as credible as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you. So what's a 15-inch shell? Well, let's think about a 15-inch cannonball, right? Fired at a piece of tissue paper. What's going to happen? It's just going to blast through the tissue paper, right? No, but sometimes it bounces back and hits you in the face. Would you be surprised? You'd be shocked and maybe dead, right? That can't happen. How could this happen? So obviously there was something wrong with the plum pudding model. What do? Well, let's make a new model, explain what's going on here. So this is what they expected would happen, that these particles would just go straight through. What actually happened is most of them did go straight through, but some of them bounced back. How could that happen? So Rutherford concluded that there must be a small, very massive area within the atom, and the rest of it's empty space. And so we now know that this is the nucleus, and that's where the protons and neutrons are in the atom, and the electrons are out here. And so this area is mostly empty space, and inside the nucleus, which is incredibly dense, that's where most of the mass is. If you were able to take just nuclei and put them together in an amount the size of a period in your book, it would weigh millions of tons. The nucleus is extremely dense. So when that alpha particle hit the nucleus, it's like hitting not a brick wall, it's like the ultimate brick wall. It's just going to bounce back. We could also think of this maybe in terms of things that are more common in everyday life. Let's think of airsoft pellets and volleyball nets. Okay? Volleyball net is just a grid made out of strings, basically. And airsoft pellets, little plastic BBs, basically. If you fire airsoft pellets at a volleyball net, most of them are going to go through, right? It's got big empty squares, right? Most of them are going to go through. But if the airsoft pellet hits the string, it's going to bounce back, right? So that's a little bit like what they were seeing here. So they said there's got to be something pretty solid in there. So from that idea, Rutherford came up with the nuclear theory of the atom. And this says that most of the atom's mass and all of its positive charge are contained in a small core called the nucleus. Most of the volume of the atom is empty space through which tiny negatively charged electrons are dispersed. And there are as many negatively charged electrons outside the nucleus as there are positively charged particles within the nucleus, so that the atom is electrically neutral. And those positive particles are called protons. Protons are positive, both start with P. The electrons are negative. So this model was very successful. It was great. It explained a lot of things, but it wasn't complete. So hydrogen atoms each have one proton in them. That's the massive particle. Helium atoms have 2 protons. So we would expect that the mass of a helium atom would be twice that of a hydrogen atom. But it's actually 4 times heavier. So what's up with that? Well, there's got to be something that we haven't found yet. So Rutherford and one of his students, James Chadwick, later demonstrated that that thing that was accounting for that mass was a neutron. So a neutron is a neutral particle within the nucleus, but it has mass similar to a proton. So neutrons have no electrical charge. They are neutral. So neutrons are neutral, protons are positive. That leaves the electrons to be the negative ones. The mass is similar to a proton. So the hydrogen atom has 1 proton and no neutrons. A helium atom is 4 times as heavy, as massive, as a hydrogen atom because it's got 2 protons and 2 neutrons, a total of 4 massive particles compared to 1. And so that explained the discrepancies in masses that were being seen. Any questions? Yeah. How did they prove the existence of the neutrons? Off the top of my head, I can't really answer that. That is a good question. There obviously was proof. I just don't know off the top of my head. This is where the idea of neutrons came from, because there had to be something in there that accounted for the variation in the masses. So the structure of the atom, we've got the extremely dense nucleus. That has more than 99.9% of the mass of the atom. It occupies a very small amount of space. We can think of a cloud. So electrons are like water droplets in a cloud. So we don't actually get to feel clouds or experience clouds necessarily, but we experience fog, right? And fog is a lot like a cloud. It's just down here where we are. So think about fog as little tiny water droplets, right? Those little tiny droplets have negligible mass, but they're dispersed over a wide area. So if you took all the droplets in the fog and put them together to condense them, that it would be a very small volume of actual water that is dispersed over this big volume, because in fog there's a lot of air in between the particles, right? In an atom, there's a lot of empty space between the electrons. So matter is actually mostly empty space. It doesn't look like empty space, right? This bench seems pretty solid, right? How's that empty space? Well, it seems solid because the variation in the density between those teeny tiny nuclei that are so heavy and all the empty space between the electrons is too small for us to see. We can think about scaffolding. They're calling this scaffolding. This reminds me of the climbing structures of my childhood. They were made out of metal, and we didn't have bark or anything underneath. There was asphalt. And they sent us out to play, and I don't think there was anybody out there watching us, and we hung upside down from our knees and fell on our heads. And most of us survived. You know, it was a different time. But imagine a ginormous jungle gym made out of metal bars. There's a lot of empty space in that. We're imagining that this is the size of a football field and 100 stories tall. That's like a climbing structure for grown-ups, right? But it's mostly empty space. When we're up close to it, like this guy is, you see that, this is mostly empty. There's just these bars. I could climb it, but it's mostly empty, right? If you zoom out or go up in a blimp or look at it from an airplane at high altitude, instead of seeing mostly empty space, you're going to see how these things overlap, and the variation in density between the bars and the empty spaces in between is smaller and smaller and smaller, and you can't distinguish it anymore, and it's going to look solid. That makes sense? So if the atom was this size, 100 yards long, 100 stories tall, the nucleus would be the size of a pea. Think of a pea, a little green pea, on the 50-yard line of a football field. That's the nucleus, where more than 99.9% of the mass of the atom is. And then the volume, the entire size of the atom goes from one goal line to the other goal line. And within that spaces are a few particles that are much smaller than that green pea. That's what an atom is. It's really kind of hard to think about. So back to the scaffolding. When you tap your knuckle on a table, what that's like is taking one giant scaffolding, your knuckle or your finger, and crashing it into another. If you took two of these and bumped them into each other, they wouldn't go through each other, would they? They would just bang into each other, even though each of them is mostly empty space. They don't fall into each other, and matter doesn't fall into itself either. Any questions? Not sure how that happened. Well, I guess it's not too far off. Okay, never mind.